Hello everyone, I am Dr. Gitumoni Sharma, Associate Professor, Department of Mathematics, USTM. Today I am going to take a class on special theory of relativity. Today's my topic is some new consequences of Lorentz transformation. Let me talk first about keywords of my lecture. Lorentz transformation, simultaneous event, and relativity of simultaneity and thought experiment. So, these are my keywords for this lecture. So, first I am going to explain about Lorentz transformation. Lorentz transformation is the relationship between two different coordinate frames that move at a constant velocity and are relative to each other. The frame the name of the transformation comes from Dutch physicist Hendrik Lorentz. There are two frames of reference which are inertial frames, motion with a constant velocity, and other frame is at rest position. So, as we discussed in our previous classes, that always consider two frame of reference. One is S frame, another is S dash frame. S frame at rest position where velocity is 0 and S dash moving with a constant velocity, and then we relate to equation and coordinate between the S frame and the S dash frame. Coordinate of the particle with respect to S frame is x, y, z, t, and with respect to S dash frame it is x dash, y dash, z dash and t dash. Then we relate a equation between to the coordinate system. Historically, the transformation were the result of attempts by Lorentz and others to explain how the speed of light was observed to be independent of the frame of reference and to understand the symmetries of the laws of electromagnetism. As we know that Galilean transformation failed to prove Maxwell's electromagnetic theory, then Einstein thought that Maxwell's theories are very important because Maxwell theory gives that light is an electromagnetic phenomenon and light has speed 3 into 10 to the power 8 meter per second. So, Einstein suggested that one new mathematical method of testing has to be derived, and that is known as Lorentz transformation. So, using Lorentz transformation equation, it is proved that Maxwell's electromagnetic theory, that is light, also same for all observer. Now, we are going to discuss about simultaneous equation. Simultaneous equations or simultaneous event are those physical events which may happen in different locations, but they happen exactly in same time. Simultaneous events are happens exactly in same time, but they happen in different location. So, for example, if you have two light bulbs and light up exactly in same time, we can say that they are simultaneous because their time is same. So, we call this example as a simultaneous event. According to special theory of relativity, simultaneous events are not absolute. What does it mean? It means for one observer in one frame of reference, there are two events which are simultaneous. It does not necessarily mean they are going to be simultaneous for in any other frame of reference. So, simultaneous events equation or events means that they are simultaneous for one frame of reference, but it is not important or not necessary to that they are going to be simultaneous for the other frame of reference. That means two simultaneous events are simultaneous only with respect to one particular observer, and they not necessarily simultaneous with respect to any general observer. Now, in this connection we are going to discuss about the thought experiment. We have a train and some kind of moving vehicle which is moving in a uniform velocity in a certain direction. Inside the train we have a light bulb. If we switch on light bulb, then light up. Light travels in both forward and backward direction. So, in this example, in this thought experiment, we consider a train and some kind of moving vehicle, and one observer inside the train and another observer outside the train, and one light bulb is here inside the train, and when the light bulb switch on, then light up and the light travels in both direction, forward direction and upward direction. there are two observers, one is inside the train and other is outside the train. Now let's look at the experiment from the perspective of both the observer. Now both observer observe this experiment, observe the situation when light travels in forward and backward direction. For the perspective of first observer, which is inside the train, light travels in both directions since light is situated in center. Since the person observed the entire setup inside the train, all the setup raised to him. So which observer inside the train, he observed that it is a race frame because the velocity is 0, and he observed the light travels in equal in both direction, backward and forward direction. Since the raised to him, now as we already know, second particle's speed of light is constant and it is therefore unaffected by the motion of the train. Since the speed of light is forward direction as well as in backward direction is exactly same, so obviously light is going to reach front end of the train is exactly the same time back end of the train. So we know that light is independent, it is not affected by the motion of the train. So according to him, he said that light is same front end and light taken the same time to reach the front end of the train and the back end of the train. So obviously light is going to reach front end of the train is exactly the same time back end of the train. Light reaches the front end A and back and reaches in B. Then the event A and B are simultaneous, but with respect to the observer inside the train. So see this picture. So first picture shows the inside that shows the observer which is inside the train, and second picture shows that the observer outside the train. So inside the train here is a light bulb, and when light bulb is switched on, then light travels in both direction, backward direction and forward direction. And according to him, according to inside observer, he see that the both event A and B. So light when reach the front end A of the train and back end B of the train, then A and B at same time. According to the inside observer, he observed that both event happens in same time. But in this picture, outside observer, he see that the light, if switch on the light, then he said that train is moving, so light also moving. So according to him, light B event is faster than the event A. So according to him, A and B are not simultaneous. For the outside observer, now what is going to happen? For an observer outside the train, train is also moving in this particular direction. So if we switch on the light, light has been emitted in forward and backward direction, but as the light is also traveling, train also has also moved in same direction. What happened is that effectively back end of train is moving towards the light and front end of train moves away from the light. So this is the main reason why this outside observer observed that both event not happen in simultaneously. So this is the picture of Lorentz transformation that apply in this event. So it is the race frame F and F dash is the moving frame. So according to him, according to F frame, it is the coordinate of a particle is x, y, z, t, and according to F dash frame, coordinate of a particle x dash, y dash, z dash and t dash. Then after derivation, Lorentz transformation are x dash is equal to gamma into x minus Vt, t dash is equal to t minus gamma into t minus Vx by c square, and gamma is the Lorentz factor. It is known as 1 by root over 1 minus v square by c square, and y and z direction are the same because they are parallel. So these are the equation, Lorentz transformation equation given by equation 1 and equation 2. Now, but we know that there are some consequences of Lorentz transformation. These are relativity of simultaneity, length contraction, time dilation. Now, we are going to discuss about relativity of simultaneity. Suppose two events occur at x1 and x2 in S at times t1 and t2 respectively according to S frame, and times S T1 dash and T2 dash respectively according to the S dash frame. So, here we consider two frame S and S dash. S frame rest position where velocity is 0 and S dash moving with a constant velocity. Now, two events consider, one is x1, another is x2, and they happen at same time, that is T1 is equal to T2. They are the time measured from the rest frame S frame, and T1 dash and T2 dash is the time with respect to the moving frame. Now, what is the time difference between between both event? So, delta T dash represent the time difference. So, delta T dash is equal to T2 dash minus T1 dash, difference between the both time which is observed by the observer in S dash frame. Now, we know that in Lorentz transformation equation, T dash is equal to, see equation number 1, time part is T dash is equal to T minus Vx by c square whole divided by root over 1 minus V square c square. So, in this equation if we put T2 dash, then we get T2 minus Vx by c square whole divided by root over 1 minus V square by c square, and T1 dash is equal to T1 minus Vx by c square whole divided by root over 1 minus V square by c square. So, we apply this formula here and we get T2, we get the after calculation we get T2 minus T1 minus V by c square bracket x2 minus x1 whole divided by root over 1 minus V square by c square. Now, there is a question that T2 minus T1 the first term. So, we know that the first time is T1 is equal to T2 because the both event occurs at the same time, therefore, T1 equal T2. So, this first term will be 0. So, we get the V by c square into x1 minus x2 whole divided by root over 1 minus V square by c square. So, it is equation number 1. So, here we have assumed that two events have occurred simultaneously with T1 equal T2 in S frame, but equation 1 shows that T1 dash not equal T2 dash in S dash frame. So, see this equation. So, we get delta T dash is equal to the A non-zero value. So, delta T dash not equal to 0. So, delta T dash means T2 dash minus T1 dash. Therefore, we get that T2 dash not equal T1 dash. So, we can say that whatever occurs simultaneously in one coordinate system is not simultaneous in the other coordinate system. So, for the first frame S frame, it is simultaneous event because x1 and x2 happens in same time, T1 equal T2, but in after calculation we get that T1 dash not equal to T2 dash, where T1 dash and T2 dash are the time measured by the S dash frame. Therefore, we can say that they are not simultaneous according to the S dash frame. So, relativity of simultaneity is one of the consequences of Lorentz transformation. It is one of the most striking consequences of the Lorentz transformation, as a universal concept has to be abandoned. Simultaneity is also relative. Before we address this, we note that the clock placed at different position in an inertial reference frame can be synchronized by using light for synchronization utilizing the constancy of its speed. So, same situation happen in case of a clock paradox. In our universe, when you sense from a non-moving perspective to a moving one or vice versa, that sense of perspective is represented by a what's called the Lorentz transformation, which is a kind of squeeze stretch rotation of space-time that we have mechanically implemented with the space-time globe. So, all of you know that our space-time is like a cloth. So, when we imagine a situation in our space-time, then some situation happens. So, when moving from a rest observer, rest particle start to move to a moving position, then some situation happen, and this situation can be shown by this diagram, picture 4. This in our space time, this situation happen in case of different type of frame of reference. A quick reminder, space-time diagram plot position on the horizontal axis and time on the vertical axis, and something moving as time passes traces out a path through space-time called world line. So, see this picture, it is time axis, it is vertical, and the space axis is the horizontal axis, and different type of events happen in according to time and space. Then one of the first things you might notice about Lorentz transformation is that events that were at different places at the same time before the transformation are not at the same time after the transformation. So, due to Lorentz transformation, they are not happens in same situation, same time. This is the picture of space-time diagram, and we saw this diagram by world line picture, and this is also known as Minkowski diagram. This means that from the perspective of people going different speeds, simultaneous events for one person won't be simultaneous for the other and vice versa. For example, if from my perspective these two boxes spontaneously combust at the same time and you are moving at a third the speed of light to my right, and then from your perspective, that is the from your perspective it is left. So, it is the picture. So, according to different observer, their situations are different. That means they are different. They are happens in differently different places and at the same time, but another reference frame of reference say that it not happens at the same time. So, this is the diagram for this. The takeaway here is that our universe has neither an absolute motion of time nor an absolute sense of simultaneous events, and that simultaneity breakdown more the further away from each other. Two things are a box even further to the left and from my perspective simultaneously spontaneously combust with the other's will. From your moving perspective be even further out of sync it with the box on the right. This is described by the time part of the Lorentz transformation equation. So, in Lorentz transformation equation we get the equation which is T dash is equal to T minus Vx by c square whole divided by root over 1 minus V square by c square. So, using this we get the time, and then we say that different frame of reference say that the events are not simultaneous. This is described by the time part of the Lorentz transformation equation. The part says that T nu is equal to gamma times T minus phi times x over square. So, this is the equation T nu is equal to gamma into T minus Vx by c square, and x nu is equal to gamma x minus Vt. So, it is observed by the new frame of reference. Because of the line x, because of the x in there, the further away an event is from you, the more each time from the new perspective will be out of sync with events closer to you. Though because of the factor of c squared in the denominator which is huge, it is hard to notice anything being out of sync until either your speed or distance to the object in equations are really big. Like you have had to be going half the speed of light and be comparing things further apart than the earth and the moon before things would become more than 1 second out of the sync. See this picture. Then here but in that case events that were simultaneous from my perspective really would be out of sync for you. As surprising as this maybe seem, it might feel more familiar and comfortable when you remember that this getting out of alignment phenomenon happens to points at the same place in space, to which is literally that what we think of as defining motion. From my perspective, this box is at same position at different times, that is it is not moving, maybe simultaneous, but from your moving perspective it is at different position at different times it is moving. See this picture. So, this is the picture of two reference frame. Simultaneity is just the other side of the coin. The fact that events that happen at the same time at different spatial position happen at different times when viewed from a moving perspective. Altogether, in our universe, the takeaway in this event that were previously either all at the same place or all at the same time get out of a alignment with each other when you sense to a moving perspective. So, simultaneity between two frame of reference. According to the special theory of relativity introduced by Albert Einstein, it is impossible to say in an absolute sense that two distinct events occur at the same time if those events are separated in space. If one reference frame assigns precisely the same time to two events that are at different points in space, a reference frame that is moving relative to the first will generally assign different times to the two events. For example, a car crash in London and another in New York appearing to happen at the same time to an observer on Earth will appear to have occurred at slightly different times to an observer on an airplane flying between London and New York. Furthermore, if the two events cannot be causally connected depending on the state of motion, the crash in London may appear to occur first in a given frame and the New York crash may appear to occur first in another. However, if the events are causally connected, precedence order is preserved in all reference frame of reference. So, it is the main reason why we are not say that two events simultaneously happen in one frame of reference and it is not necessarily that they happens simultaneously in other frame of reference. So, here some situation given between A and B. Even B is simultaneous with A in the green reference frame, but it is occurred before in the blue frame of reference and will occur later in the red frame of reference. Again, some explanation by the Einstein about the thought experiment. Einstein imagined a stationary observer who witnessed two lighting balls simultaneously striking both ends of a moving train. He concluded that an observer standing on the train would measure the balls to strike at different times. Einstein's version of the experiment presumed that one observer was sitting midway inside a speeding train car and another was standing on a platform as the train moved fast. As measured by the standing observer, the train is struck by two balls of lighting simultaneously but at different position along the axis of train movement back and front of the train car. In the inertial frame of the standing observer, there are three events which are spatially dislocated but simultaneous. Standing observer facing the moving observer, lighting striking in front of the train car and lighting striking the back of the car. Since the events are placed along the axis of train movement, their time coordinates become projected to different time coordinates in the moving train's inertial frame. Events which occurred at space coordinates in the direction of train movement happen earlier than events at coordinates opposite to the direction of train movement. In the moving train's inertial frame, this means that lighting will strike the front of the train car before the two observers align. It is the picture when time t is equal to 0, then light switch on, and then at t is equal to 1, its light travels in both direction, and at t is equal to 2, light reaches the front end of the train and back end of the train. And according to Einstein, he said that it happens as he inside observer, so he said that both event happens simultaneously. It may be helpful to visualize the situation using space-time diagrams. For a given observer, the t-axis is defined to be a point traced out in time by the origin of the spatial coordinate x and is drawn vertically. The x-axis is defined as the set of all points in space at the time t is equal to 0 and is drawn horizontally. The statement that the speed of light is the same for all observer is represented by drawing a light rays as a 45-degree line regardless of the speed of the source relative to the speed of the observer. So, word line, we know that word line is at 45-degree angle, and according to this, when this experiment happens, so three situation happens here. When time t is equal to 0, at time t is equal to 1, and then t is equal to 2. In the first diagram, the two ends of the train are drawn as grey lines because the ends of the train are stationary with respect to the observer of the train. These lines are just vertical lines showing their motion through time but not space. The flash of light is shown as the 45-degree red lines. The points at which the two light flashes hit the ends of the train are at the same level in the diagram. This means that the events are simultaneous. So, thought experiment, same explanation according to Einstein experiment. The space-time diagram in the frame of reference on the train. In the same diagram in the frame of an observer who sees the train moving to the right. In physics, the relativity of simultaneity is the concept that distance simultaneity, whether two spatially separated events occur at the same time, is not absolute but depends on the observer reference frame. This possibility was raised by mathematician Henry Poincare in 1900 and thereafter became a central idea in his special theory of relativity. So, these are the picture of different situation. Thank you.